Right, okay. So our next speaker, and indeed our host, is Artem Lopatin from Campinas. That's the best I'm going to do on that pronunciation. And he's going to be talking about pairs of matrices with a simple spectrum.
Okay, thank you for the introduction. So I would like to say that the title of my university is Universidade, Estadual de Campinas. And so it's State University of Campinas. Of course, you can pronounce it in this way in Brazil. But like months ago, we were told that nowadays, from this point, we should always write it down as Universidade Estadual de Campinas. So it's like official name now, not the University of Campinas, not State University Campinas, but written in Portuguese. So that is why it's written in Portuguese. Okay, so here's the title of my talk. It is joint work. So here's parts of my talk. So it's joint work with Jennifer Juliana Calderon Moreno from Colombia. And so I will try to be a little bit fast because we have some small time issues, yes, and so I will omit some details, but here I guess everybody knows all these details. So here I work over an arbitrary field which can be finite of arbitrary characteristic, and so I consider a very classical situation which has been considered already. So we have a tuple of m n by n matrices. We have tuple of n by n matrices, and of course we have general linear group which acts by conjugation, by diagonal conjugation. Of course, it's very classical action with many applications. For example, it corresponds to the situation when we have n-dimensional vector space and we have m linear maps on it, and we are changing basis, and we see what's going on with the matrices, which defines these maps. And it's very well known that the problem to classify orbits with respect to this action is impossible to a certain extent. For example, it's a wild problem. And I'm not going to go into details what exactly means impossible here. I just want to say that there is so-called two-sided Curto-Herrero conjecture. Original Curto-Herrero conjecture was formulated in 1985, but it can be also considered so-called two-sided variant of it, which I'm going to consider now. And so our conjecture is the following one. We have two tuples of matrices, and these two tuples belong to one and the same orbit. If only for any non-commutative polynomial in any variables, we have that rank of fa is equal to rank fb. So what exactly does it mean? So we consider any polynomial, and instead of variables, we put elements from the first tuple and then from elements from the second tuple. And if the rank of the corresponding matrices is the same, then this conjecture claims orbit will be the same. So it looks very nice conjecture, but it has some little problem that in general it is not true. So it was established by Hedwin and Larson in 2003 that for two 3x3 matrices, this conjecture fails. And so this conjecture fails, then why did I mention it? Well, because in general it's wrong, but in some particular cases, this conjecture still may be true, and these particular cases may be of some interest. For example, we don't know, does it hold or not, or at least I don't know, does it hold or not for 2x2 matrices. And actually it looks like very interesting and probably simple, maybe not simple, I don't know, problem to verify this conjecture for m tuples of 2x2 matrices. It may be true, or it may fail, I don't know. And there is a very trivial case when it definitely holds. It's the case of one matrix. It's in case of algebraic closed field, it's just a Jordan normal form. But it also holds if the field is not algebraically closed. All we need is a rational canonical form of a matrix, and we immediately obtain it. So here there is some very recent result which has some connection with all this discussion, and it's a paper published in Advances in Mathematics by Derson, Kleb, Makame, and Volchich, I guess, who is here at the moment, and he will talk later today, that if we consider these tuples of matrices, that their orbits coincides, if we consider so-called matrix non-commutative polynomials. And so the ranks are the same. What here does it means? What does it matrix non-commutative polynomial? It's a matrix which is built of polynomials. So each element of this matrix is a polynomial. And so we put as elements in these polynomials matrices, we obtain matrix of matrices. And so ranks, if ranks are the same, then they belong, these two tuples, they belong to one and the same orbit. And in this paper, there are some, I guess, some restrictions to the degrees. Okay, but now we are coming back to our situation, which is different. And so we are, as I said before, this conjecture, two-sided Curto-Herrero conjecture, may be valid in some partial cases. And that's exactly what we're going to do. We are going to consider some partial case. And we will show that in this case it holds, and we establish some additional restrictions to the degrees of polynomials which we have to consider. And so this partial case is the following one. We consider pairs of matrices, so we just work with pairs of matrices, and we have condition on the first matrix that its spectrum is simple. It means that it has n distinct eigenvalues. Or it can be diagonalized, of course, with any different numbers on its diagonal. And so because it has any pairwise different eigenvalues, of course, we require that our field F has any pairwise different elements. And so, of course, yes, and we denote this set by Dn. Of course, it's Gaussian submodule of pairs of matrices. And actually, orbits, Gaussian orbits on this set, they were classified around 10 years ago by Futornikov and Sergeychuk. And so we are going now to consider the results with some slight modification which we will need for our purpose. And so this classification is done by means of the following two parameters. The first parameter, it's directed graphs without undirected cycles. So it's graph, it's directed, but if we consider its arrows simply like edges, then it doesn't have any cycle. And so this graph is called type of canonical pair. And we also, for a canonical pair, we will consider a certain number of parameters. These parameters, they can take arbitrary values from the field F, and so they are called free parameters. And so orbits are parameterized by canonical pairs, and so canonical pair is given by type, which is essentially speaking graph, and by some parameters. Later, I will come into details and explain exactly how it works. Okay, and so now I'm going to start with more detailed explanation. First of all, I need the notion of star matrix. So star matrix is n by n matrix, which is made of 1, 0, and star. So each element is just 0, 1, or star. So we can think about this matrix as some formal matrix where star just symbol, or we can think about this matrix as a subset of n by n matrices, where in case we have 0, all elements of these subsets, they have 0. In case 1, all elements of the subset, they have 1 in this position. But in case this star matrix in some position has entry equal to star, it means that there can be any element. There can be any element. So here we don't have any restriction on an element of matrix A in position ij in the case there is a star in this position. So we will think about star matrices as subsets of n by n matrices and as some abstract matrices. We can do both things. And so in case some entry of star matrix is a star, and then we say that Aij is a free parameter. It's free parameter. And so now some definition about graphs, which of course are very well known by everybody, but I just need to fix them. And so by graph, we mean directed finite graph. And here it's important that its vertices are numbered. So for example, so this numeration of vertices is fixed. And for example, graph 1, 2, so with arrow from 1 to 2, and graph V0 from 2 to 1 are considered different because numeration of vertices is different. So we denote by these vertices, by this way we denote arrows. And so graph without undirected cycles, of course, is called forest. And we have also definition of a tree. So if two vertices in a forest are connected by undirected paths, it's a tree. And over a set of all pairs of vertices, we fix some lexicographical order. It can be any lexicographical order, for example, this one. And so now we are going to define key notion of canonical star matrix. So canonical star matrix. So we consider star matrix as you remember, it's n by n matrix with three types of elements, with 0, with 1, or with star. And so it's called canonical if we can correspond a forest to it with vertices v1, v2, vn, so it has n vertices, such that we have the following list of conditions. So from first glance, this list of conditions maybe look a little bit difficult, but actually after, I don't know, reading it, it becomes quite simple and straightforward. So the first condition is the easiest one. So we have that if there is an arrow from vi to vj, then the corresponding entry, so entry ij of star matrix is equal to 1. So we put ones where we have arrows. Let me now consider the last condition. It's also quite simple. So aii is always star. So on the diagonal of this matrix, we have stars. The second and the third condition are a little bit more complicated. So what do we have here? So we have aij is equal to 0 if we have the following condition. So G has no undirected path from vi to vj. If it holds, then aij is 0. But it could be that this condition doesn't hold. And so it could be that there exists a unique undirected path from vi to vj. But if we have the following condition, so this path is denoted by a. Yes, so a is a path. And so if this path a contains an arrow vr, vs, with this condition that rs, the pair rs is greater than the pair ij, so with respect to the lexicographical order which was introduced on the previous slide, then we still have 0 in this position. But in case we have this undirected path, but this condition fails, then we have a star. So here we have two cases, either this case or that case. And depending on it, we obtain 0 or star. And finally, this condition has already been considered. And after quite straightforward and not a very difficult consideration, we can see that actually, so here we have some forest, that there is one-to-one correspondence between star matrices, which are canonical, and all forests with n vertices. So of course, from the definition follows we have star matrix, then we obtain some forest, but if we have some forest, we obtain a unique star matrix. So it's one-to-one correspondence. And for example, the following lemma, if we have A and B, two n by n canonical star matrices, then if we consider them as subsets of n by n matrices, then these two subsets have have empty intersection in case these two canonical star matrices are different. And so now we have key definition of canonical pair. So we consider a pair from Dn. So it means, I will repeat that the first matrix has n different eigen values, and the second matrix doesn't have any restrictions. So we write down the first matrix like diagonal one, and we can order elements of it because on the field F we can always introduce some relation, and we don't require any additional conditions on this relation. Just for any two element from the field, we can say if one is less or another one is less. That's it. We don't require any additional conditions on this relation defined over the field F, and we can always introduce such a relation over any set. And the second matrix A2 belongs to some canonical star matrix A. So here, canonical star matrix A we consider as a set, and then this notation that A2 belongs to A, it makes sense. And so, because here we have canonical star matrix, we have corresponding graph. We denote it by GA, it was denoted by GA, and it's called type of this canonical pair. And so here is a key definition of canonical pair, and this theorem by Futorny-Horn and Sergeychuk of 2011, it says that the set of all canonical pairs on Dn is in one-to-one correspondence with Gillian orbits on Dn. So, of course, it means that any orbit contains a unique canonical pair. We can consider example. It's quite easy to consider examples here. For example, we consider 2x2 matrices. Then what kind of canonical star matrices we have? Well, to see what kind of canonical star matrices we have, we should start with forests without cycles, oriented cycles. So first such graph is a graph with just with two vertices and no arrows at all. So now we consider canonical star matrix which corresponds to it. On the diagonal we have stars, as says the first condition from the definition of canonical star matrix. And because we have no arrows here, then non-diagonal elements are zeros. And so we have star matrix, and we have the corresponding graph. In case the graph have just one arrow from V1 to V2, what do we have? On the diagonal, we still have stars, but since we have an arrow from V1 to V2, then in the position 1, 2, we have 1. And straightforward consideration will show us that here we have star. And in case we have an arrow from V2 to V1, then we'll get 1 in this position. On the diagonal, we have stars. And straightforward consideration of conditions from the definition of star, of canonical star matrix, will imply that here we have 0. So these are all canonical star matrices for case of 2x2 matrices. And we can proceed like this, let's say for 3x3 matrices and so on. For example, let me consider the case of n equal to 4. Of course, here the list of all canonical star matrices is quite long, but we can consider some of them. For example, if we have V1, V2, V3, V4, then on the diagonal, as usual, we have stars. Then we have here 1, 1, 1, obviously, and the simple consideration implies that here we have zeros, and underneath main diagonal we have stars. And similarly, we may consider this example. So here we have 1, 1, 1, here zeros, and here zeros again, Okay, so now I'm going to introduce very well-known definitions of coordinate algebra. So I guess everybody knows what it is. And then we define the action of GLN over this coordinate algebra, because in our case, we may have that the field is finite, then we use symmetric algebra. I mean, it's usual definitions, so it's the usual action. And so we got polynomial matrix invariance here, okay? And algebra of invariance, okay. We have generic matrices as usual, and then we'll need subalgebra generated by generic matrices. We denote it by this, and together with identity matrix. So there is this result, which has already been mentioned by Sibisky-Procesi, and in case of positive characteristic by Donkin, that the algebra of matrix invariance is generated by coefficients of characteristic polynomial of products of generic matrices, as we all know. And now about abstract invariance. So what do I mean by abstract invariance? So we have polynomial invariance. Of course, we may consider rational invariance, but here I'm making a little bit further step by considering abstract invariance. So we consider all functions from m tuples of n by n matrices to the field F, and denoted by F and M. And then we say that what is the algebra of abstract matrix invariance? It's the set of those functions which are constant over orbits. So we can pick up some element from M tuple, take any element from group G, and we got this equality. It means that this abstract function have one and the same value over all elements of the orbit. And we call this element abstract matrix invariance. Well, of course, polynomial invariants are abstract matrix invariants. We can consider some other abstract matrix invariants. For example, in case of just one matrix, we can define this function, which is 1 if matrix is 0, and which is 0 if A is not 0. And of course, it's abstract matrix invariant. And we can define some other functions like rank. With rank, actually, there is some tiny technical problem which we can resolve by doing the following things. And so the problem is rank. It is not a function from this set. Why? So rank of matrix is not an element from the set because rank is a function from the matrices to integers. And field F may not contain integers. Let's say field F may be a field with 2 elements. And then, of course, rank is not abstract invariant. Clearly, we can maybe change the definition of abstract invariance, and here instead of field F, consider, let's say, arbitrary ring or arbitrary ring, but I don't want to change it. I would like to keep it this way. And so then to do it, we can do quite trivial trick. We can define rank with T. It's a function which is equal to 1 when rank is T and 0 otherwise. Then obviously this rank T is a abstract invariant, and we have that rank of A and B is equal when we have this equality. So it allows us to continue to work with abstract invariants. Okay, and then for any polynomial, for any element in the algebra generated by generic matrices, we may define this element CF, and we may define rank F. And it is easy to see that the result is abstract invariant. Okay. And if field F is infinite, then it is easy to see that, for example, this abstract invariant is not polynomial invariant. It's trivial fact. Okay, then technical definition. If you have some abstract invariant, we may define its width as small as d, such that there exists an abstract invariant with defined over d tuples of matrices and some elements generated by generic matrices and some elements generated by generic matrices, such that we have this equality. So essentially speaking, the width, what does it mean? It means that how many matrices we should consider, and using the composition with elements from the algebra generated by generic matrices. For example, if we consider sigma t, it's a coefficient of characteristic polynomial, then of course it has width 1, and rank, it has width 1 as well. And okay, now consider A and B, 2 elements from Dn, and with the property that eigenvalues of A1 are not the same as eigenvalues of B1. Then obviously A and B are separated by coefficients of characteristic polynomial, which is trivial fact. Okay, and so now some terminology about separating invariants, but we will apply them to abstract invariants. So we have some subset of abstract invariants, and we say that this set separates Gillian orbits on m tuples of matrices. If for any A and B from n by n matrices, we have that the condition f A is equal to fb. It implies that orbits are the same. It applies that orbits are the same. And so, given a Gillian invariant subset, we may define a set when a set or S separates Gillian orbits on L. Okay, exactly in the same way. Exactly in the same way. Okay. So here, idea is that we not necessarily consider all M tuples of matrices. We just consider some subset of M tuples of matrices. The subset, of course, would be Gillian invariant, and we consider separating subset for this particular Gillian module. The notion of separating invariance, of course, was introduced by Derksen and Kemper as some independent notion, and they studied some properties of it. But in some particular cases, the notion of separating invariance has been around many years before them, of course. And we also very well know that separating polynomial invariants, they do not separate all orbits, they just separate orbits closed in the Zariski topology. And so now, finally, we will consider our results. So our first result is the following one, that two-sided Courtois-Herrero conjecture for the space Dn of pairs of matrices holds. So namely, the following set at the center is a set of all ranks of F, where F is an element of algebra generated by two generic matrices, and it has degree less or equal to n plus 1 multiplied by 2n minus 1. And so this set separates all orbits. Then we can say and obtain this corollary just we can just rewrite theorem 1 because this corollary says exactly the same in slightly different words. So we can take abstract invariance of bits 1. So here they are given, and we can separate all Gillian orbits on Dn using this set. Okay. And then we have another result about separating types. So as I hope you remember that canonical pairs are given by types and some parameters. So we may ask a slightly different question: how to separate types, because types are quite important for some properties and so on. And so here the set is given. So this set sigma together with this set, they separate all types of elements of Dn. So here we have some stronger restriction on the degrees of polynomial. And so this element is just equal to 1 or 0, depending if corresponding matrix is 0 or non-zero. And so all types can be separated by this set. And of course, this set is not enough to separate all orbits. Is essentially the following lemma says. It says that to separate of orbits, this set is not enough. We should consider bigger set, which was given in corollary and in theorem 1. So that is it. Here, a list of some references. These are paper is in archive. It's been submitted some time ago. And so thank you for attention. Okay. Are there any questions? I mean, I can't hear anything. Okay. Is John here? Well, if somebody have question, it is possible to ask. Yes, Ben, you can ask a question.
I just wanted to ask this combinatorial, star matrices and the graphs part of the talk. Can you say anything about intuition for why the list of how to construct the star matrix from the graph had this complicated step where if RS was lexicographically greater than such and such, then it was, I forget if it was a 0 or a star or what, but can you say anything intuitively about why that is the right way to construct the correspondence?
Well, you can, let's say, try to read the corresponding paper by Futorny, Sergeychuk, and Horn. They didn't use the notion of star matrix. They use slightly different terminology, but for our purposes, it's better to use the notion of star matrices. Yes, and so it is the right way because. So I'm going to open the definition of canonical star matrix. Yes, it is here. So it is the right way for the following reason. We have this action of Gillenormand pairs of matrices, and we have like some procedure which we can use to try to define canonical form. What do I mean by that? I mean, the first matrix, of course, is diagonal. It has n pairwise different elements. And then we conjugate this matrix. It's fixed, yes, by some matrix. And when it should be fixed by conjugation. It's some restriction. It puts a very solid restriction on the matrix which we use for conjugation. And so model this restriction, we consider now the action of this matrix with restriction action on the second matrix. And then the nature of this restriction actually implies that we can use some algorithm, like step by step, depending where we have in the second matrix, where we have zeros or non-zeros. We are trying step by step to obtain its canonical form, and so it's quite natural, this definition. So this definition is a result of this process of finding canonical form. Let's put it this way. And so it turns out that we've got this one-to-one correspondence between these canonical star matrices and all forests, which is quite nice, I think.
Perfect. Thank you so much. That was super helpful.
Okay. Jonathan is not here. I don't know. Okay, then
I am sorry. I am here. I was just on mute.
Okay, so there has already been one question by Ben.
Yeah, I heard it. I even contributed, and nobody heard me. Okay. Well, I don't think we've got any further questions. So